Today, we want to consider a hemispherical bowl with a radius of 7 centimeters, and it's going to contain a mysterious liquid to a depth of 5 centimeters. And we want to find the volume of the liquid in the bowl. The reason I refer to this as just a mysterious liquid is that it's going to have variable density. That's why I had to draw this liquid in Disney green, that evil Disney green. Once something glowing green shows up in a Disney movie, you know that's the bad guy. So we're going to have a variable density show up as the second part. So we haven't even revealed the villain yet. But I mean, we all know. It's kind of like a Scooby-Doo episode. There's nothing really mysterious going on. The thing that we changed in this problem from our previous problem, even though our side view looks the same, we're still looking at a circle. Now, when we take a slice of that circle, that slice is not going to represent a rectangle. The slice represents a circle. That slice is a circle. So the area of the slice will be pi times the radius squared. The area of the slice is pi r squared. Last week, we were looking at a cylinder. This week, we're looking at a hemisphere. So now when we think of this horizontal slice, that horizontal slice will be a circle. So instead of having a width times a length for the cross section, I'm going to have pi r squared for the cross section. So we have to know where the radius is of our cross section. We're going to calculate the volume of the slice the same way that we always do in this kind of problem. We're going to take the cross-sectional area and multiply by the height. Now, the cross-sectional area is continuously variable. The size is always different, but the shape is always the same. That's why I get to write the volume of the slice as the cross-sectional area, pi r squared, times the height, delta x. Because this is our strategy for integration. We deal with the continuously variable factor by making it constant for a little while. Because if we make the delta x small enough, the radius won't change that much. We know from our previous problem that when we're looking at this side view, this circular side view, we make a right triangle to get a relationship between our horizontal and our vertical variables. Make a, oh no, that's going to be fine. We make a right triangle to get a relationship between the horizontal and the vertical. That right triangle has to go from the center of the circle because we need a constant hypotenuse. The important thing to note is that the bowl is hemispherical. The liquid is not. The liquid is not a hemisphere. We don't take can't take an orange. If we cut it right down the middle, we have a hemisphere. If we take that hemispherical orange and cut a slice off the top, we do not have a hemisphere anymore. So although the water here has a depth of 5, we do not necessarily have a radius of 5. It's not 5 going all the way around. If we want to use a right triangle to get a relationship between our vertical and our horizontal, we have to go from the center of a circle, not the surface of the water. So the important thing to note here is that the liquid does not form a hemisphere. The depth of the liquid is 5, but it is not a hemisphere of radius 5. Otherwise, I wouldn't have the bowl in the first place. So what's left to do is assign our variable x. Delta x is, we made our delta variable vertical. So x has to be some vertical distance. That makes sense. Our radius is some horizontal distance. We're going to need a vertical distance for the depth. The most reasonable place to put x is from the top of the bowl. That's what we've done in the past. One of the legs of the right triangle is r. The other leg of the right triangle will just be x. So let's make x the distance from the top of the bowl down to the slice. Once we label a variable, we have decided where 0 is and which direction is positive. So our choice indicates that 0 is up at the top of the bowl. The bottom of the bowl will be at 7. And more importantly, since we're going to integrate where there's water or where there's liquid, the liquid doesn't start until 2. So the 5 centimeters of water are x equals 2 to x equals 7. Now we can pull out that right triangle and get a relationship between r and x. Now I can pull out this right triangle. Our radius down here. Our vertical variable x. And our hypotenuse of 7. So this says that r squared is the square root of 49 minus x squared. Or sorry, r is the square root of 49 minus x squared. And then that will go in for our r in the volume of the slice. Now we finished the development phase. We have our diagram, we have our development. Next thing is the definite integral. The important part of the definite integral, the primary thing you want to get is the correct interval on your definite integral. The secondary thing is to simplify your expression. So my V total, I'm going to factor out the pi, but I'm going to simplify the expression. The square root of 49 minus x squared is just going to leave me 49 minus x squared. So our secondary goal is to simplify the expression. Even though we're going to be typing this into our calculating machine, we should simplify our expression so we have to type less. Third thing that we want to make sure we get right is our discrete delta x should become the continuous dx. If you write a definite integral with a delta x in it, I'm probably not even going to notice. If I take off points because you wrote delta x in your definite integral instead of dx, if I took off points for that, I must have been in a foul mood. And you should be like, oh, hey man, are you okay? Because you took off points for me writing delta instead of dx. And I'll be like, oh, yeah, you're right. That sucks. And I put the points back. The important part of the definite integral is integrating the right 5 centimeters from 2 to 7 and not 0 to 5, depending on how you set up your. Set up your variable x. Don't set up your x. That's not right. That's like a crime. I didn't write it here, but if I was typing out this problem for you to submit to me, I would have said round your answers to 5 significant figures, which is your cue to just use a machine, even though this would be a super simple integral to integrate. We've got a math 9it of 40 of pi. Yeah, whoops, I left that out. I'll put it in at the end. Oops. So since I said round to 5 significant figures, the first step is to indicate that that means I want you to use a calculator. The second step is to be kind of annoyed that I gave you 2 significant figures and I'm asking for 5 in your answer. So you can go ahead and be annoyed by that. If you want to indicate that you are annoyed by that, you could always put your exact value. So to just comply with the instructions, you'd write 418.88 cubic centimeters. If you put 418.88, I 100% would not notice. I forget the units almost all the time. I never make units. If the units are part of the problem, then I will say indicate units in your answer. Usually that's when you're interpreting what a definite integral represents. But I said find the volume, so these are going to be volume units. Now you might be looking at these cubic centimeters and they're like, oh, dude, this is liquid. Why not use milliliters? Go ahead and use milliliters. I do the math thing and just write cubic centimeters. So if you want to be stubborn, you could always just write the exact value. So we got 400 over 3 times pi. So if you're like, oh, no, this is going to be a fraction multiple of pi. Any questions? How's that, bro? Okay. These particular pens do not like being vertical when they write. They also have a speed limit. Like if I try to write too fast, it will not be able to spit out enough ink or gel. Oh, earlier I had mentioned that the liquid does not form a hemisphere. Notice that when x is equal to 2, this relationship must hold. So the radius of the circle at the surface of the water will be the square root of 49 minus 2 squared, or 6.71. That is not 5, so it is not going to be 5 all the way around. So it's not a hemisphere. In the second half, almost not quite. In the second half, we're going to change things up a little bit. The main thing that's going to happen is that we're going to define a function where 0 is at the surface of the water. Sorry, the strange green liquid. So remember, we have an uncountable infinity of places we can put our variable. In this case, there are only 3 that make sense: the top of the bowl, the bottom of the bowl, the surface of the liquid. The second one is going to involve the surface of the liquid. And I'm just gonna define it right now. Oops. See, this is what happens when I go out of order. So what we're going to do is we're going to set up a variable density for this liquid, where the density at the surface will be, let's say, 1, and it will increase it'll increase to 1.5 at the bottom. So it'll increase by a tenth. So we'll have a variable density that increases as you get deeper. So maybe there's some stuff in here and it's settling out, making the liquid denser at the bottom. I don't know. I'm not a chemist, nor am I a physicist. I just want the variable to the density to be variable up and down. So let's suppose that the density let's suppose that the density of the liquid at a point y centimeters below the surface of the liquid is given by this function. I think it's 2 plus 1/10 of a y per grams per cubic centimeter. So at the surface, the density is 2, but then the density increases as we go deeper to 2.5 at the bottom. So in this problem, the variable y was given to us. We were told to use this variable y. Y is the distance from the surface of the the surface of the liquid down to the bottom or down to the slice. So what that means is that 0 is now at the surface of the liquid. The bottom of the bowl is 5. And the top of the bowl is -2, but we're not going to care about that. Because when we're integrating, we want to integrate where there is liquid, not where there is empty bowl. So the 5 centimeters that we're going to be, the 5 centimeters of depth that we're going to be integrating is gone to 0 from, is now 0 to 5. Note that some of the things are the same. We still want the radius of this slice. We're still going to draw a right triangle measured from the that gives us a constant hypotenuse, which has to be from the center of the hemispherical bowl. So our radius r, where previously the vertical leg of that right triangle was x, it's not y. Y goes from the surface, not the top of the bowl. So I need an expression for the vertical leg of this right triangle. So I've got a 7 for our hypotenuse. Our radius is r. But our vertical leg is not y. Y starts here at 0. The top of the bowl is at -2. So this distance that we want here is y plus 2. So our radius is the square root of 49 minus y plus 2 squared. All we did was shift where 0 was. So we know that we can substitute 1 or dy integral into the dx integral. If x equals y plus 2. If x equals y plus 2, then instead of integrating from 0 to 5, we'll integrate from 2 to 7 like we did in the previous problem. It's all connected. But in this second part of the problem, I don't want you to find the volume of the liquid. We already have that. Since I introduced the density, I want you to find the mass of the liquid. In this case, we're going to use mass is equal to density multiplied by volume. Our density is variable, and our volume is also, well, our volume is fixed, but our density changes with the volume. So the mass of the slice will be the density of the slice multiplied by the area of the cross section multiplied by the height of the slice. So we're going to take the density of the slice multiply by the area of the cross section multiplied by the height of the slice. We need to finish, we've got our diagram. We're not finished with our development because our density is in terms of y, but our radius is not in terms of y. That's why we needed that triangle. That's why we needed the center of the hemisphere. So I'll have the density 2 plus 0.1 y times pi times the radius squared times the height. Then for our total mass, there's 3 things that we need to do. Most significant, get the interval correct. We're going to be integrating from 0 to 5. Number 2, we're going to simplify our expression so we have to type less. And number 3, our delta y needs to become a dy. Else I'll take off 1 billion points. I'm just kidding. We're going to factor out the pi because we like to factor out our constants. We have our density is a function of y, so that can stay. The square root of 49 minus y plus 2 squared will just give us the 49 minus y, the square of y plus 2. Delta y will become a dy, and we're integrating from 0 to 5 for the depth of the water. I suppose we can simplify this more, but I don't want to simplify this more. The main thing I want to avoid is having to type a square root in my integral. So I will math 9. 2 plus 0.1 x times 49 minus the square of x plus 2 with respect to x from 0 to 5, close parentheses. We need to multiply by pi. So 913.03 grams. If I want to write the exact value, that'd be 2325 over 8 pi. And now it's starting to look weird. I'm not sure when the 400 over 3 looks weird to me. It's weird to write fractions of pi when when the numerator is 3 digits and the denominator is just 1 digit. Like if it was 40 over 3 times pi, that would be like more acceptable. But as soon as it's like 400 over 3 times pi, that starts to look weird to me. I'm like, well, why are we doing this? And then if you wrote 2325 over 8 times pi, because that's our coefficient of pi in this case, I would definitely think that looks weird. I wouldn't take off points, but if you come up to talk to me after class, I will take a step back. Like, oh, wait a second, you wrote 20, you think it's okay to write a fraction of 4 digits over 1 digit. What's your question? And then you're like, turn your angle, your tablet towards me. I'll be like, no, I can see it, I can see it. I'm like looking over at it. Do you know what I mean? I'm just kidding. Write your fractions how you want. That's just local weirdness. One of those inexplicable things. I'm like, oh, that looks, see, like this, it was hard for me. It was legitimately hard for me to write 400 over 3 times pi. 400 over 3, that's perfectly fine. If the answer was just 400 over 3, I'd be all right with it. I'd like 400 over 3, 133 and third. But because I was writing this as a fraction multiple of pi, I didn't like it. And I'm not sure why. I think it's because I'm in a trig class. And it's like, well, let's cut off a bunch of whole circles, but that's not what we're doing here. So how many times can we subtract 2 pi from all this? So that we're just having like one of our 60-degree reference angle. You'll notice I can't even bring myself to write 2325 over 8 pi. Actually, it's because I'm out of space. It's like nice spacing up here, crap spacing down here. It's all crammed up. Is it still called kerning? Because I know kerning is how far apart you write stuff this way. Is it still kerning if it's like up and down? Anybody graphic artists? Tattoo artists? Doesn't matter then. Now, in this case, our density was given to us with this variable y. So we have some baggage going on here. You were handed this variable y. And it's kind of messed up the way I gave you these problems, because I set the problem up. I gave you this problem. I warned you that I was going to give you the density. It's going to be a function of the variable under the surface, but then I saddled you with this variable y. Now we could, if we had already found the volume, this 400 over 3 times pi, rather than going and resetting everything to be in terms of y, we could just reuse. I'm not going to draw the whole thing. I'm just going to draw in the highlights. we could reuse, so our y was the distance from the surface down to the slice. Where at the surface we're at y equals 0. And down here at the bottom is where y is equal to 5. Originally, we had done the problem in terms of x, where x was measured from the top of the bowl. As we saw when we were doing our calculation for the radius, we could just substitute x is equal to y plus 2. So the distance from the slice to the top of the bowl is just y plus the 2 centimeters from the surface to the top of the bowl. So x is equal to y plus 2. That's why our radius was the square root of 49 minus y plus 2 from 0 to 5 instead of the square root of 49 minus x squared from 2 to 7. It's just a 2-unit shift. Since x is equal to y plus 2, I can rewrite the density by saying that y is equal to x minus 2. And I could rewrite our density in terms of x as 2 plus 0.1 times y, which we can replace with x minus 2. In this case, we would just be modifying our volume definite integral to incorporate this new information. This new information tried to saddle us with another variable, and you could say, no, I'm going to use the variable that I've been using all along. I'm going to translate the density to fit the variables that I've already set up. So your total, well, let's go with the mass of the slice, will be the density 2 plus 0.1 times x minus 2 times your area, pi, times the radius, square root of 49 minus x squared. And now the problem's back to being a delta x problem. So instead of having y and y plus 2 squared, we have x minus 2 and x squared. And then our total we'll still take out the pi. For some reason, the only thing I'm going to simplify is just the square root part. I spend so much time doing this, even though we already know what the mass of our of the liquid is, because knowing the mass of the liquid is not the point of the problem. Setting up definite integrals is and understanding the process of integration is the problem, and this is how we can bring substitution up, even though we're not using the technique to find an integral. So this integral gives us the same result, which is important. If these two integrals gave us different results when they're supposed to represent the same thing, one of them has to be wrong. It could be that both of them are wrong, but one of them has to be wrong. This is a calculation. This is an observation about something that is. We don't get to agree to disagree. Any questions? How's everybody okay? Math class just too easy? Is that the problem? So simple. It's elementary. Sometimes I get asked, Leach, why do you not grade on effort? And it's very simple. I don't grade on things that I won't observe for every student. So, like take what I just said, for example. So some students, it's very plain that they're working very hard. Maybe they're like at my office hours every single day. Every time I walk by the STEM center, they're sitting there asking questions and getting a lot of help. And I could see the amount of effort that they're putting in. Some students will go through great lengths to hide the effort they're expending from me for whatever reason. That's your own psychology. I don't do psychoanalysis, but some students feel compelled to act tough and not show weakness. I think that's where it comes from. And so I don't watch that whenever that they, because they don't study in the STEM center where they think I might see them working very hard. They don't ask me any questions. They find someone else, someone disconnected from me so that it won't get back to me that they're asking questions. Some students hide that from me. And that's okay. If that's the way that you want to go through it. I mean, you hired me to be as a resource for a reason. I don't know why you would want to tell me that you don't know how to do stuff. I mean, I know that. That's why you hired me in the first place, but that's all beside the point. You're trying to project an image, and I don't want to take that away from you. So I don't see that you're working very hard. Now, let's suppose that these two students get the same result. They both worked just as hard, but one, I was able to observe them working hard. The other one, I was not. They both worked just as hard, and they get the same result. They're both sitting at 88%. Let's make it like 87%, where it's like really questionable. It's like, oh, should I bump them up? If I take the student who I saw work hard and bump them up to an A, and not this other student at the same result, I'm 100% in the wrong. I fucked up because I'm grading on something that I didn't observe and didn't observe for everybody. You know what I mean? What I can observe is the result that you put up for your homework. I can't observe whether it's you that put that result up or it's your cousin who's like already an engineer, but I know it's not your cousin who's already an engineer because engineers can't fucking do calculus for shit. So I know it's not them. But maybe you have like a cousin at another school who's also in calculus, who's like a couple of sections ahead of you. So like, oh, dude, here's how you do this problem, or here's what those is. I can't tell. I mean, if you're going to do that, then I don't know. Why are you here? What's the point? But anyway, at least on the surface level, I can say, this is your work. You got these answers. You produced this result. That's what I can score you on. Does that make sense? So that's why I don't grade on effort. Any teacher that does grade on effort is necessarily being unfair to some of their students. And it's teaching students performative things. Like, well, if this teacher is going to grade on effort, that only effort they can see, then I have to demonstrate that I'm putting in an effort. Here's another reason I don't grade on effort. Let's suppose two students, they ended up at 87%. One of them worked very hard. It could be one of the previous students that worked very hard. Spent extra hours every day. 2 hours per hour in class? Nah, like 4 hours per out of class per hour in class. They get an 87. I have another student that doesn't have to do anything. Does all their work, but just breezes this class. Some of you are going to be in that category. You have not reached the class that's going to challenge you. You haven't reached the math class that's going to challenge you. And you're just like barely putting in enough effort. You're like barely showing up to class. Like every day you come into class, you're like, what are we doing? Volume? Okay. And then you just fall asleep. And you land at 87%. I give those two students different results. For what? They both pulled an 87. Just because one student didn't work hard, I need to discriminate against that student because of their talent. Or let's suppose that that student has been in my class before, and I know they could have done better with a little more effort. Do I give them an A just because I know that they're talented? No, that is also bullshit. I grade the result. What did you turn in? Then I look at what's the highest grade in the class. If the highest grade in the class is 87, that's got to be an A. If the highest grade in the class is 87, okay, I was the kid. So maybe that's me. I must have been asking some challenging questions. If the highest grade in the class is 87 and it's my classroom, you should be like, oh, damn, we must be pretty good because Leach is putting this challenge up to us. He's throwing a lot of challenge our way. He must think something of us. You know what I mean? All right, anyway. Look at the see the substitution. See the thinking behind this. Continuously variable, we make it constant for a little bit. That's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.